Hi, welcome to another video on analog electronic circuits. In this video, we'll see some basic concepts of MOSFET and its circuits. So let me see. Of course, in this entire video, we'll be assuming Kp of NMOS transistor as 200 microampere per volt square and the threshold voltage as 400 millivolt. Similarly, for PMOSFET, that Kp is considered as 100 microampere per volt square and threshold voltage is minus 400 millivolt. Now, in the first problem, we are asked to find the change in drain current of the circuit shown below if R2 changes from 100 kilo ohm to 110 kilo ohm. So we are asked to find what is the value of change in ID if this R2 is changed from 100k to 110k. Of course, this is R1, R2 along with VDD is used to provide the VGS, the required bias potential for this. And of course, we have a WBL of 80 for this particular MOSFET, and we have a drain resistor connected with 1 kilo ohm. So as we know, the drain current, so let us assume the MOSFET is in saturation region, because now since we are dealing with analog electronic circuits, we are considering the MOSFET to be in saturation region. So we are considering the equation of the drain current in the saturation region, which is given by this expression. So in which we know all the values, Kp we know, WBL we know, VGS also we know, and VTH is also known. So VGS is nothing but a potential divider using R1, R2 and VDD, so which can be easily found as 600 millivolt. So upon substituting these values of Kp and all this stuff, we are going to get the value of ID as 320 microampere, which is a very easy calculation. Then what is interesting is, so if we change the value of R2 from 100k to 110k, what is the change? So now we are changing this R2 to 110k. So that's what is this. If R2 is 110k, the VGS becomes 638 millivolt from 600 millivolt. The corresponding ID is this 453.15 microampere. So it has changed from 320 to 453 microampere. So that's what we are trying to see, what is a percentage change in VGS. So now as the value of R2 changes from 100k to 110k, so there is a 10% change in the value of RD. That results in 6.33% change in the value of VGS. So which is obvious here. What we are doing is the higher voltage minus 0.6 divided by 0.6. So this is the percentage change. And the corresponding change in the current, so which is 453 corresponding to this VGS and corresponding to 600 600 millivolt of VGS, we had 320 microampere. So this is the percentage change in the current in ID is actually 41.6%. So which is a considerable change. So how do we see this change in VGS, which is hardly 6.33, but the change in ID is almost 41%. So as we know, the relationship between this ID and VGS, so ID actually is proportional to square of VGS. So that's what is this relation what is telling. So ID is proportional to square of VGS. So percentage of change in ID will be equal to percentage change in VGS square. That is square of the percentage change, which is obviously here 6.33 whole square is around 40.66. So whatever change that we are getting as 41.6 percentage change against 6.33 percentage change in VGS is obvious over here. So the summary of this entire simple problem is, if VGS changes, then ID changes by VGS whole square. So that is one of the change, one of the observation. And then here you can see we have a similar circuit, except that here we have a RS of 100 ohm. So again we are asked to find the value of change in ID whenever R2 changes from 100k to 110k. It is similar to the previous problem, but only thing is that there is an emitter degeneration resistance of source degeneration resistance RS that is added at the source. So let us see the impact of this RS in the circuit. Again, we do the same analysis. Assuming the MOSFET in saturation region, we write the expression of ID is equal to half Kp WL into VGS minus VTO whole square. Again, when I say VTO, VTH all are same. So now we are substituting VTH of NMOS transistor, which is 0.4. But if you can see, the VGS is the VG voltage the gate minus voltage at the source, because source is not grounded. So we have a voltage at gate which is VDD R2 by R1 plus R2, and the voltage at the source is actually the current flowing through this resistor multiplied with the resistance, which is ID into RS. So that's what we are trying to find. So with R2 as 100 kilo ohms, the value of VG becomes 0.6, and of course you are using this equation. So what we actually do is, of course, since we know how to use the calculator effectively using that alpha A, all those stuff, the value of ID comes out to be two different values. So one of the possible values 246.09 microsecond, other one is 16.25 microsecond. These are the two mathematical uh, solutions. Out of this, okay, 246 microampere is a valid answer, because you cannot have this much current. If this much current flows, then MOSFET is in linear region. Not only in linear region, it is not possible to have that much current with 1.8 as the voltage there, as the VDD. So we are considering this as a valid current. So when we actually see this current, now this is the current what you have. So if you can see, VG is this much. So since I know the current, I can actually find out how much is VGS is. So VGS comes out to be, of course, now you know this is VG. As you know ID, you can also find what is VGS. So VGS comes out to be 0.575 volt. And then, so we are recalculating the value of ID with R2 is equal to 110 kilo ohm. So when R2 changes to 110 kilo ohm, the VG changes from 0.6 to 0.638 volt, and you again refine the value of ID. So it comes out to be 336 microampere, and of course these are the two possible values, out of which this is a valid answer. So now you can see this is a change in VG from 0.6 to 0.638. Corresponding value of change in VGS is from 0.575 to 0.601. So this is for a change of 10% change in R2. You can have a close look at this. So now we have, what is the percentage change in ID? Percentage change in ID is from 336. Of course, this is for a larger value of R2. This is for a lower value of R2. When you find the percentage change, this comes out to be 36.7%. What is the percentage change in VG? The percentage change in VG is 630, okay, 6.33 as it was earlier. But you can see the percentage change in VGS has reduced. The percentage change in VGS has reduced. Now, what is the summary of this entire analysis is, the moment you have this RS, the source degeneration, as in the previous case, the value of R2 is changing by 10%. Whenever this value changes by 10%, you have a 6.33% change in VG, but VGS changes lesser percentage. So VGS changes by hardly 4.78%. The advantage or the importance of looking at this RS is, whatever change that happens here, due to the presence of this RS, the change in VGS is not like 6.33% as it was in the earlier case, but it has reduced to 4.78%. So because of this reduction, you can see the percentage change in ID has also reduced from 41% to 36%. The entire concept behind this is, if we use a RS, that is source degeneration resistance, the drain current will not be changing such drastically compared to the value of, okay, a circuit without having this source degeneration. So that's what the summary is. You can see here, use of RS reduces the percentage change in ID from 41.6% to 36.7%. This is the advantage of source degeneration. That is, source degeneration is used to stabilize the amplifier performance against the bias condition variations. Because when you change R2, the bias condition will change. the change in bias conditions will certainly affect your ID, but that effect of change in bias conditions is bit reduced because of the value of RS, because of the presence of RS. Suppose if you change the value of RS from 100 ohm to 200 ohm, you can still find, okay, this will be slightly different. You can just give it a try. So what you can do is, so you can make this 200 ohm, try to find out how much is the change in ID compared to 100 ohm. So, but to have a better and better, okay, immunity over the changes in the bias conditions, the designers will decide what is the value of RS, so that the amplifier or the circuit is stable against the changes in the value of R2 or any of the biasing conditions. So that's what the entire purpose of doing these two things. So let us go back to simulations and then try to find out what is that we have observed, is it true or not. So let us do the first simulation of this circuit. So here when you change it from 100 kilo ohm to 110 kilo ohm, the ID changes from 320 to 453 micro amperes. Let us see this. Okay, this is the circuit what I have. So let me just make it. Now I can see this is 200k, this is 100k, this is 1k, and W by L is 80 here. So as we wanted, and of course I'm writing a similar circuit, but this is changed to 110k. All other things are remaining constant. If I run now, okay, let me. This is, you can find the different values of VGS, VDS, and of course you can find the ID also. But it's better you just view in this, okay, spice output log. Can you see for the first MOSFET, we found the current to be, if you just go back and see, so what is the current here? It was 320 microampere. In the other case it was 453 microampere. Can you see the same currents are there? Can you see it is the same? Can you see it is 320? Okay, where is that? It went here. This is 320 microampere. Can you see this is 453? Okay, this is slight, okay, maybe 3 microampere difference is there because we have truncated the value of VGS while calculating. So this is what is the value of ID for first case, and this is for the second case. And you can find, okay, all other values of VGS is there from 600 millivolt to this is 639 millivolt. So this way you can able to confirm yourself, okay, whatever calculation that we have done over here is matching perfectly with the simulation results. Let us do it for the other one. Where is the other one? So other one, we have it over here. Okay, now let me see the other one. So now, okay, let me so this is the other circuit. Can you see here? So we have other circuit where, okay, what I'll do is I'll just, for the time being, I'll just delete this so that you can see only the, okay, now you have this circuit. So now what is this? This is 200k, this is 100k, and this is 1k. What we are changing is, here we are having a 100 ohm resistor. So now the result of this should be something like this. So we had this one now. So let me just minimize this. So this is what is 100 ohm. You can see this is 100 ohm, and we are supposed to get a current of 246 microampere and 336 microampere. So these are the currents that are expected from this simulation. You can see we got these two are also as your solutions, mathematical solution, but in the simulation you'll get only these two currents because this is not an electrical answer. So let me run that and see. Let me run it. Sorry, that dot op is missing. So let me just do this dot op, do this, and then let me run this. Okay, no analysis is found. Okay, dot op is still missing. Okay, I will select this, do this, and then show it. Okay, now this is your dot op. Okay, these are your different DC voltage and currents. Let me go to this view and then see this output log. See now here, do have a current of 246 microampere and 336 microampere, which is as we obtained in our equation. Can you see it is 246? This is 246. This is micro. This is 246 micro here. This is 336. This is also 336. microampere. So this is how you can see VGS is, that's what is VGS is 0. It is 575 here. You can see it is 604. Can you see it is 575 and 605? Of course, hardly 1 or 2 millivolts difference will be there, so that's not a big thing. And you can see the MOSFET is in saturation region because VDS is far greater than VDS sat. So VDS sat is hardly 175 millivolt, but you have 1.53 volt as the VDS value. So this is how you can able to confirm that okay, whatever calculations that you have made here are correct. Let me just put back the circuits and then okay, let me have the circuit here. Let me save it. Let me go to the next set of problems. So next problem what we have is, now we are asked to find the change in the value of ID when RD changes from 1K to 1.5K. So this is a circuit what you have. So now in the previous case we saw the change in the value of okay, R2 and the corresponding value of ID. Now we are keeping R1 R2 constant. We want to change the value of RD from 1K to 1.5K. We want to see what is the change. So now again, as we did earlier, assuming MOSFET in saturation region, I'm writing the saturation equation. VGS is can be easily found out from this okay, VDD R1 R2, which is using this equation, and VDS at is this much. As you can see, how much is this? So ID comes out to be 552.55 microampere. With RD is equal to 1K, VDS is equal to 1. Of course, VDS you can find, which is nothing but VD minus ID RD, which comes out to be 1.2475 volts, which is far greater than VDS at. So MOSFET is in saturation region. So when you change this RD from 1K to 1.5K, you refine the value of VDS. You can see now VDS comes out to be 0.971, which is still certainly more than VDS at. So MOSFET is still in saturation. So even if the value of RD is either 1K or 1.57K, the current remains as 552 microampere. So as long as the MOSFET remains in saturation region, this value of RD will not change the current. That's what is. No change in ID of 552.55 microampere as RD changes from 1K to 1.5K because the MOSFET remains in saturation region for both the values of RD. So let me just go back to my circuit and try to find out what it is. Where is that? Here, this is my second circuit. Let me just open that. I'm opening my second circuit. Is my second circuit? No, this is here. So we have it here. So see here, this is 220K. Okay, let me just for the time being delete this. Let me take it up later. I'm deleting. So let me just move this from, sorry, let me move this from here to here. Let me zoom it out. This is you can see this is, if I will just compare that with my circuit, this is 220K. Let me see, this is, can you see here, this is 220K, 120K, 220, 120, and this is 1K, and W bell is, you can see W bell is 100. So L is 1, W is 100, so W bell is 100. So now everything is done. Again here this is made 1.5K. So naturally we saw in the solution that okay, no current changes because the same 550, how much is that? Same 552 point something microampere current will flow. So let me run this and try to see again. You can see this is 553 here, 553 here. Let me just see it in the output log. See here, is this my output? If you can see, both the currents are 554 microampere. This is 554 microampere. Of course VDS has slightly changed, but it is certainly more than VDS sat. So that's why MOSFET currents are same if the value of RD changes from 1K to 1.5K. The summary of this entire thing is, as long as the MOSFET remains in saturation region, this RD will not change the value of the current flowing through the MOSFET. That's fine. So now let us go to the fourth one, and it's the same circuit. You can see it is 220k, 120k. This is 1k, and this is WL is 100. But the change what we have from the previous problem is that, so this is again 220k, 110k. Now you are changing the value from RD of 1k to 5k. So what is the change? So we already know that when it is 1k, the rest the current is how much? Now I think we have changed it to, okay, now this is 110k. So okay, fine. So I just want to have a different VGS. So this is now 110k. We are changing the value of RD from 1k to 5k. So when it is if this is the value of VGS, which comes out to be 0.6, VDS at is of course 200 millivolt. The ID comes out to be 400 microampere. So let us try to find out with this 400 microampere flowing through this, is the MOSFET is in saturation. So that's what we are trying to find out. So with the ID as 400 microampere flowing through this MOSFET, so let me just zoom it out. See, now this is 400 microampere flowing, so it is 400 millivolt drop. So 1.8 minus 4, 0.4 is 1.4 volt. So VDS is this much, but VDS at is hardly 200 millivolt. So VDS is greater than VDS at. So ID is equal to 100 microampere, that is ID sat. The moment I change this RD from 1k to 5k, can you see this becomes minus 0.2 volt? So you cannot have a VDS which is negative in a circuit. So then ID of 400 microampere is not possible to flow. So this is not a valid current now. So what we simply did is we simply substituted the same value of ID as in the previous case to see what is the VDS. But when VDS comes out as negative, or if it is less than VDS at, then you cannot assume that much current is flowing through the MOSFET. So then certainly MOSFET is not in saturation region. So then when it is not in saturation region, I need to find the linear current. So this is ID linear, which is given by half kpw into L 2 VGS minus VTO into VDS minus VDS square. So this is the expression what I have. Now upon doing the calculation, so we got the value of ID as 336 microampere as well as 300 microampere. Now in the previous case, you can see when we are actually finding, in the previous case we had these two currents. Let me just go back here. So when we had a calculation here we had two currents. So we could able to certainly neglect this milliampere current and we considered this. But here in this problem, you can see you have two currents, which is 336 and other is 300 microampere. So it becomes a doubtful which one is a possible current. So either you can select this or this, because both are valid even electrically and mathematically. So in order to find out which current is even if, okay, 336 flows or 300 microampere flows, VDS will be less than VDS at. So MOSFET is in linear region. Which current to consider? So I have picked this 336 microampere because I did a simulation and found that the ID is also. So of course in such type of problems it may be slightly difficult to choose a current which is very close to this. And of course, even if you choose 300 microampere or 336 microampere, it's not an issue. So now I'm selecting 336 microampere because in my simulation, I got that as my current. So let me go to this and see what is. Let me just do undo. See now, this is my circuit. This is my second circuit. Maybe I can delete this so that we can see only the fourth thing. Okay, I'm just retaining that. Now you can see this is 200, 220k, this is 110k, this is 1k. Now you can see this is 5k. The WL is still retained as 100. WL is still retained as 100. If I run now, this I'll get it as 400 microampere. This I'll get it as 336. Now here this is in saturation region, but this is in linear region. So that you can see it here. So now let me just close this, go to this view and output log. See here, can you see this is 4 point into 10 power minus 4 is actually 400 micro. Can you see it is 3.36 into 10 power minus 4 is 336 microampere. So in the solution we got both answers, 336. Of course here though it's only one answer, because since you didn't had any ambiguity, this is only one answer. Since we have VDS and that VDS need to be substituted as VD minus IDRD, when you solve this using calculator, we got this as the valid current. You can see VDS is 0.12, that is 120 millivolt, whereas VGS is how much? VGS is 0.6. So VDS sat is 200 millivolt, whereas VDS is 120 millivolt. So that's why MOSFET is in linear region. So you can just go back and check the simulation results also. Can you see that this is VDS? VDS here is this is 1.4 volts. This is 120 millivolt. So that's why here M7 is in saturation, whereas M8 is in linear region. So whatever current that you are seeing here is the linear current. Whatever current that you are seeing here is the saturation current. Can you see here? This is VD sat. VDS sat is 200 millivolt. Here also VDS sat is 200 millivolt. There is no change in VDS sat because VGS is 600 millivolt only. But VDS in the first case is 1.4 volt, which is more than 200 millivolt. The MOSFET is in saturation region. Whereas in the second case, VDS is less than, of course, VDS is 120 millivolt, which is less than 200 millivolts. So that's why MOSFET is in linear region. So that's what the solution here. So what is the solution of the fourth problem? So it says that as RD is equal to 1 kilo ohm, MOSFET is in saturation region with a current of 400 microampere. Whereas when the value of RD is 5K, MOSFET is in linear region because VDS is less than VDS sat. So VDS is 120 millivolt, 0.12 volts. Hope okay, this will give you some confidence in understanding what is why the current changes, what is the change in current when the value of VGS changes. So if you just go back to the summary of this entire thing, so we actually took different problems where we had in the first case this is changed from 100 to 110 kilo ohm, and we saw there is a 40% change compared to 6.3%, that is square of the VGS change. And here with the value of source degeneration, we found that the effect of change in R2 has reduced the change in the effect of your ID because of this source degeneration. And in the third case, we found that this RD is not changing the value of ID because MOSFET is remaining in the saturation region. In the last problem, we saw the MOSFET current, or the drain current of this MOSFET is controlled by ID because the MOSFET is moving from saturation region to linear region because of this increased RD. Because why it goes to linear region is because the voltage across this drain and source reduces less than VDS set. Okay, that is conceptually the MOSFET and its biasing. Hope okay, you will get these concepts.